On the previous set of boards, you'll recall that operators theta I star were used to construct matrix factorizations of corresponding to a decomposition or a presentation of the polynomial as a sum of products. In this set of boards, I'll say a bit more about the background which is used to construct such operators, namely exterior algebras. So I'll start with some definitions about algebras. Our base ring will be a commutative ring, K. And recall quickly the following definitions. So a K algebra A is a K module which is also a ring such that the two structures are compatible. That is, R acting on A times B is equal to A multiplied by R acting on B is equal to R acting on AB for all R in K and for all AB in A. Equivalently, there's a ring homomorphism from K into the center of A. A Z-graded K algebra is a K algebra A equipped with a direct sum decomposition as an abelian group. The elements of A sub D are called elements of degree D. Such that the identity is of degree 0 and the product of elements of degree D with elements of degree E is of degree D plus E. I'll flag that by an algebra here I don't necessarily mean a commutative ring. So K is commutative, but the algebras may be non-commutative. Okay, such an algebra is called graded commutative. And I'll just abbreviate this to GC. If given homogeneous elements A and B, so that is, this notation here just refers to the degree, so that's another way of saying A belongs to A sub A and B belongs to A sub B. Okay, so A and B commute up to signs. And, oops. And I'll also ask that homogeneous elements of odd degree square to 0. This follows, if the character, if 2 is invertible, this follows from the other condition, but otherwise it may not. Okay, so that's a graded commutative K algebra. One way to introduce the exterior algebra is to describe its universal property. So I'll do that briefly first for those of you who find that appealing. So you can consider the category of K modules and the category of graded commutative K algebras. So it's a category that has objects, the graded commutative K algebras, graded K algebras, as I just introduced them. The morphisms are degree-preserving morphisms of graded algebras. So there's a functor which just extracts from a graded commutative algebra its degree 1 part, and that's a K module. And you can prove that that functor has a left adjoint, and that left adjoint is called the exterior algebra. So in terms of a universal property, that characterizes the construction. Now let me tell you the more down-to-earth set theoretic description of the exterior algebra. So given a K-module M, the exterior algebra is the tensor algebra of M, so that's a non-commutative K-algebra, modulo an ideal. It's the two-sided ideal generated by the tensors X, tensor X, where X ranges over all elements of M. Okay, so you take that set, you take the two-sided ideal generated by it, and the quotient is an algebra by construction, the exterior algebra. Right, so recall the tensor algebra is just as a direct sum. It's K plus M tensored with itself plus M tensored with itself 3 times, and so on. Now observe that in this quotient, X plus Y tensored with itself is 0. But in the tensor algebra, that expands. So this is for X and Y and M. As shown. So that shows you that if I write square brackets for the classes modulo the ideal I, it shows you that X tensor Y is equal to negative Y tensor X. So the elements X and Y anti-commute, because this is the product, of course, taking the tensor. They anti-commute as elements of this quotient. So usually we write the product in the quotient using the wedge. So the equivalence class of X tensor Y is written as X wedge Y. Okay, so that constructs the exterior algebra as a K-module. Since I is clearly a homogeneous ideal, it's generated by homogeneous elements, the quotient acquires a grading from the grading of the tensor algebra. So the canonical Z grading of the tensor algebras give this part degree 0, this part degree 1, this part degree 2, and so on. And that makes Tm into a graded K-algebra in the sense I described earlier. And the quotient is also a graded K-algebra with the same grading. So the elements of M viewed as elements of the quotient have degree 1. The elements of M tensor M have degree 2, and so on. So notice that the calculation I did on the previous board to show that elements of M viewed as elements of the exterior algebra anti-commute, that is X wedge Y is equal to minus Y wedge X, shows that in fact the exterior algebra is a graded commutative algebra, if you think about it, because every element can be written as a product of those things which come from M. So the exterior algebra is a graded algebra, and moreover, using the universal property, that's the best way to do it, you can check that the construction of the exterior algebra is in a sense exponential. It sends sums to products. So what I mean is that given K modules M and N, there's a canonical isomorphism of graded algebras like so. And from that, it's easy to see that if M is a free K-module, then the exterior algebra of M has the following form. So suppose we have a free K-module M with basis x1 through xp. then the exterior algebra is a free K-module of rank 2 to the p, so we denote the graded pieces of the exterior algebra by putting a superscript on the wedge. So I claim that each of these graded pieces is free of rank given by the following formula. The free rank is P choose D. So this is for D between 0 and P, and the degree D piece of the exterior algebra is 0 for D greater than P. Moreover, a K basis for the degree D part of the exterior algebra is given by the following set of wedge products of elements of the basis xi1 wedge ... wedge xin, where n is greater than or equal to 0, so the convention is that n equals 0 means that I take the basis vector, which is just the empty wedge product, which is just the identity in the exterior algebra. So n is greater than or equal to 0, and I guess I should take n less than or equal to p. And I1 up to In is an ascending sequence of indices in the appropriate range. Okay, so that set clearly has size P choose D, and that gives a K basis for the dth degree piece of the exterior algebra. So next I want to talk about operators on the exterior algebra. So I'm going to keep the same setting as in the lemma. So here M is a free K-module on the basis x1 through xp. So there's two natural operators on the exterior algebra, and in some sense these are the only operators on the exterior algebra. The first is kind of obvious, that is just multiplication, that is wedging. So given a vector in M, I can consider the operator of wedging or multiplying on the left by x. So this is a K-algebra. Multiplication is certainly K-linear, but notice that since x has degree 1 as an element of the exterior algebra, this operator of wedging on the left by x is a degree +1 operator. It sends homogeneous elements of degree d to homogeneous elements of degree d + 1. The more interesting operator is dual to this multiplication operator, and it works as follows. Given a dual vector, so M star here just means K-linear maps from M to K. Given a dual vector, eta, there's an operator called contraction with eta, which again is a K-linear operator on the exterior algebra. Turns out to have degree -1. I'll give two descriptions of it. The first is the, let's say, smart or sensible definition, which works as follows. So consider, I guess I'm saying D, aren't I? Consider the degree D piece of the exterior algebra. Now, taking the exterior algebra is a functor. Taking the degree D piece of the exterior algebra is functorial. So sending M to wedge dm is functorial, and I can apply that functor to the isomorphism between D and its double dual. So there's a canonical isomorphism, recall M is free, between M and its double dual. Now it turns out there's a canonical isomorphism between the exterior algebra of the dual and the dual of the exterior algebra in the case where the module is free. So I can take one of those duals outside. Now, notice that wedging with eta gives a map like that. Because eta is an element of M star, so the exterior algebra of M star I can multiply on the left by eta. And then if I apply the dual to that left multiplication by eta, I'll get a map. Well, notice that it sends, how should I say this? Elements of degree d minus 1 to elements of degree d, because eta has degree 1. And applying the dual, I'll get a map back the other way. So that goes to eta to the d minus 1, M star star. So this is eta wedge blank star. And then I can just put everything back in again. I can pull the star back inside. And then I can take the eta to the d minus 1 applied to the inverse, the isomorphism of M double star to M. And that composite, if you chase it around, is the definition of contraction with a one form eta. Okay, so the less smart way is to just write out what it does on a basis, which I can do. So it sends one of these basis elements that I described earlier to the following linear combination. J. So times the basis vector I get by leaving out the jth guy. Okay, so the way to read this is look at one of these basis vectors, then imagine taking that eta and applying it to every one of the vectors in that wedge product. When I apply it to the first vector, I get an eta of xi1 and no sign, because j will just be 1 in that case. And then as I move it through, moving the eta past the earlier parts of the wedge product picks up -1 signs. And by the time I've got in here to the jth basis vector in the wedge product, I've picked up a sign for all the j-1 things that came before it. And the hat here means leave this out. So maybe I should give an example. If I took the dual basis vector, which was x1 star, and contracted it with x1 wedge x2, I would get x1 star applied to x1, which is 1 times x2, and then I would get minus x1 star applied to x2, which is 0, so I just get x2. Okay, so essentially what this does is looks inside the wedge product and deletes x1 if it exists. If you have a wedge product with no x1s in it, then x1 star will always give you 0 when you consider this term. To return finally to the subject of matrix factorizations, let's continue with these operators and let me observe the commutation relations between them. So let's write theta I for left multiplication by xi on the exterior algebra, and theta I star for this contraction with the dual basis vector xi star. I claim these satisfy the commutation relations set out in board number 3 of the last set of boards, namely theta I, theta j plus theta j, theta I is 0 for all pairs ij. Similarly for the theta I stars and theta j stars. And this relation is delta ij. Okay, so I won't do the calculation, but I'll walk you through why that's true. I mean, this is clear, because this just comes from multiplication with the xi's, and xi and xj anti-commute in the sense that in the exterior algebra, xi wedge xj is equal to minus xj wedge xi by construction. Now here's where being smart gets you somewhere. Now if you wanted to check that relation just from the explicit form of the definition of the contraction on a basis, I mean, you can just go do the calculation. It's not very inspiring, and you'll see that it's true. But from the smart construction, you see that it's in fact true for the exact same reason the first set of identities is true, because contraction is just multiplication in the dual. So of course it satisfies the same relations. For the final set of relations here, this is the smart way to see this, is that contraction is a graded derivation, and you can see that from its construction using the relationship between the exterior algebra and its dual, but also maybe you should just check that directly. So it's perhaps instructional to check this relation directly on the basis to see why it's true. And I'll leave you to do that. I'll just go on to the example. So if I take M to be free of rank 2 on a basis x1, x2, then the above gives me operators theta 1, theta 2, theta 1 star, theta 2 star, acting on the exterior algebra of M. The exterior algebra of M, of course, has a basis which is given by 1, x1, x2, and the wedge x1, x2. So it's a rank 4 free K-module on which I have these operators. And if I call this basis B, say, notice that the matrices of these operators, the matrix of theta 1 with respect to this basis, what does it look like? Well, here's 1, x1, x2, x1 wedge x2. So it sends 1, of course, to x1. It sends x1 to 0 because x1 wedge x1 has to be equal to minus x1 wedge x1. Or if you like, I'm in trouble if the characteristic is wrong there, so maybe I'll say it more correctly. The ideal we modded out by to form the exterior algebra actually set x1 wedge x1 equal to 0, right? Okay, so that's 0. If I wedge x2 by x1 on the left, of course I get the fourth basis element. And if I wedge x1, x2 on the left by x1, I get 0 again. Okay, so you can go through and write down the matrices for the other operators, and you'll get these 4 by 4 matrices with 1s and minus 1s in them that satisfy these relations. So these are the promised 4 by 4 matrices which can be used to construct matrix factorizations given a decomposition of your polynomial that looks like into 2 factors. If you had more factors, then you just need more thetas, so you would take a larger rank free module M. Okay, so that wraps up the discussion of the exterior algebra, contraction, wedging, and how to use those operations to construct matrix factorizations.